The vastness of reality appears infinite, galaxies stretching endlessly, stars igniting in the darkness, and laws of physics unfolding with a precision that suggests an underlying order. But what if this apparent order is not simply the fabric of existence, but the output of something deeper, something hidden? What if behind every particle, every vibration, and every cosmic event lies a framework, a structure that resembles not raw reality, but lines of code running a grand simulation? This idea, known as the simulation hypothesis, challenges our most fundamental understanding of existence, raising the possibility that what we perceive as reality may be nothing more than an elaborate program. With that said, let us begin. To understand the simulation hypothesis, one must first grasp the essence of what it proposes. At its core, the idea is deceptively simple: the universe, with all its galaxies, black holes, and subatomic particles, may not be an independently existing reality. Instead, it could be a vast, computational construct, a simulation designed and maintained by forces beyond our comprehension. This is not a new idea of imagination alone, it finds echoes in philosophy, science, and technology alike. Ancient thinkers once speculated whether the world we perceive is but a shadow of a greater reality. Today, that question has evolved into a modern, digital form. Imagine a simple computer program. It runs rules, processes data, and generates outcomes. Now extend this concept to its furthest extremes. If technology is advanced enough, it could simulate not just a landscape or a single environment, but an entire universe, complete with galaxies, stars, and life. Within such a system, the inhabitants would have no means of discerning that their reality was not the original. They would see the laws of physics as natural, while in truth, those laws are nothing more than encoded algorithms. The precision of mathematics in nature gives weight to this possibility. The universe behaves with remarkable consistency. Gravity, electromagnetism, and quantum interactions all follow patterns that can be described through elegant equations. These equations, while profound, resemble the clean logic of programming: inputs, processes, outputs. Even randomness, such as quantum uncertainty, could be the result of intentional design, like a random number generator built into the code of existence. Critically, the simulation hypothesis raises profound questions. If reality is indeed code, then who or what authored it? What purpose does such a simulation serve? Is it an experiment, a form of entertainment, or something far beyond our ability to conceptualize? And if this universe is code, could it, like any program, experience glitches, crashes, or intentional rewrites? Such questions elevate the hypothesis beyond speculation, transforming it into a subject of deep philosophical and scientific exploration. If the universe is a code, then the origins of that code become the greatest mystery of all. One must ask, when did the program begin? Was it at the instant we know as the Big Bang, or was that event itself just a boot sequence in a vast operating system of reality? The concept of a simulation suggests that the beginning of our universe was not a spontaneous explosion of energy, but the initialization of parameters, constants, laws, and conditions chosen with precision, like variables in a grand script. Consider how fine-tuned our universe appears. Physical constants, such as the strength of gravity, the charge of the electron, or the rate of cosmic expansion, exist in incredibly narrow ranges that allow stars to form, planets to stabilize, and complex structures to emerge. A slight deviation in any of these numbers, and the cosmos as we know it would collapse into chaos or fail to exist at all. To some, this fine-tuning suggests intention, as though someone or something calibrated the simulation settings. This leads to the unsettling idea that the Big Bang was not the start of everything, but merely the loading screen of a much deeper system. If so, then everything we know, our galaxies, our planets, even time itself, may be one version among countless iterations. In this framework, alternate universes may not just be speculative theories, but different runs of the same simulation, each with modified parameters, each testing new variables. Such a thought reshapes how we view creation. Instead of asking why did the universe come into existence, we might instead ask why was it programmed? The difference is subtle, yet profound. It replaces the randomness of chance with the deliberation of design. And if there is design, then behind that design lies a mind, an intention, or perhaps even a civilization so far advanced that the act of creating universes is no more remarkable to them than running software is to us. Evidence for the simulation hypothesis, though debated, emerges from surprising places. One of the most compelling is the uncanny resemblance between our universe's structure and computational systems. When scientists map the cosmic web, the vast network of galaxies and dark matter, they find patterns that resemble neural networks, like those in the human brain, or digital circuits within a computer. This resemblance may be coincidence, but it raises a striking possibility: could the architecture of the universe itself reflect the structure of an underlying code? Furthermore, at the smallest scales of physics, reality behaves in ways that resemble digital processing rather than analog flow. Quantum mechanics, with its discrete energy levels and probability states, feels less like a smooth continuum and more like binary code, on and off states, ones and zeros. Particles exist in superpositions until measured, collapsing into defined states only when observed. This is eerily similar to how information is rendered in a simulation. Graphics appear only when a player looks at them, conserving computational power by rendering only what is necessary. Even the concept of the Planck length, the smallest possible unit of measurement in the universe, suggests a kind of resolution limit. Just as pixels define the sharpness of a digital image, the Planck length could represent the smallest pixel of reality. Below it, space and time may lose meaning, as though reality itself is quantized into a finite resolution, no different than the frame rate and texture limits of a computer-generated world. These parallels do not prove the simulation hypothesis, but they provide fertile ground for speculation. If the universe is indeed coded, then these discrete limits, these quantized layers, and these structured patterns may be the fingerprints of its programming. They might be subtle clues left behind, like artifacts in a digital file, reminding us that reality may not be as solid as it appears. If we accept the possibility of a coded universe, then the question arises, can a simulation ever reveal its own glitches? In digital systems, no matter how advanced, errors occur. Programs freeze, data corrupts, and anomalies appear where the rules of code break down. Could our universe, too, contain such anomalies, moments where the program falters and the underlying framework reveals itself? Some researchers and thinkers point to phenomena in physics that defy easy explanation. For example, the mysterious nature of quantum entanglement, where particles separated by vast distances seem to communicate instantly, appears to break the established rules of locality. In a coded system, however, such behavior could simply be the result of shared lines of code, two variables linked in the same programming structure, updating simultaneously no matter the distance. Another curious example lies in the so-called fine structure constant, a number that governs the strength of electromagnetic interactions. Measurements over cosmic history suggest this constant may not be perfectly constant after all, it may shift ever so slightly across time and space. If confirmed, such a discovery would imply that the very rules of physics are not fixed, but adjustable, like parameters being tweaked within a simulation. Beyond the realm of physics, there are also strange psychological and perceptual phenomena often described as déjà vu, synchronicity, or improbable coincidences. While easily dismissed, these experiences invite speculation. Are they simply glitches in the rendering of our lived experience? Is déjà vu a momentary error in the processing of memory, akin to a frame repeating in a film reel? If glitches exist, they are subtle, hidden within the complexity of reality. Yet even their possibility suggests that the boundaries of our universe are not immutable. They hint that the code may not be flawless, that somewhere deep beneath the surface, the program of existence may ripple, stutter, or reveal its seams. The simulation idea becomes even more intriguing when viewed through the lens of quantum mechanics. At its core, quantum physics describes a reality that seems unfinished until it is observed. Particles exist as waves of probability, capable of being in many states at once, but collapse into a defined reality only when measured. This process has baffled scientists for over a century, yet in the context of the simulation hypothesis, it takes on a strikingly familiar form. In computer simulations, environments are often not fully rendered until the player interacts with them. A distant mountain in a video game may not exist in detail until the character approaches it, only then does the system allocate resources to display it. Likewise, the quantum world may operate in a similar way, where probabilities remain undefined until an observation forces the system to render a final outcome. What appears to us as uncertainty might instead be an efficient computational strategy, ensuring that energy is not wasted calculating every detail at once. Entanglement, too, resembles this logic. In digital programming, linked variables can change instantaneously, no matter their virtual distance. If reality itself is a coded system, then entangled particles are not communicating across space faster than light. They are simply two outputs tied to the same underlying instruction. From our perspective, it appears miraculous. From the system's perspective, it is nothing more than efficient coding. This interpretation does not strip away the wonder of quantum mechanics, it deepens it. For if the universe is operating like a computational system, then each quantum experiment is not merely probing particles and waves, but pressing against the very architecture of the code itself. The laboratory becomes not just a place of discovery, but a potential window into the programming of existence. Beyond physics, mathematics itself lends unsettling support to the simulation hypothesis. Mathematics is not just a tool we invented to describe the universe, it seems to be woven into the very fabric of reality. Every natural phenomenon, from the spiraling arms of galaxies to the rhythm of planetary orbits, follows mathematical laws with stunning precision. But why should the cosmos adhere so strictly to numbers? In a coded universe, this puzzle finds a natural answer. Code itself is built upon logic and mathematics, binary systems run on the language of numbers. If our universe is a simulation, then the omnipresence of mathematics may simply reflect the fact that the universe is generated by rules and algorithms. Equations are not human constructs, they are the operating system of existence. Consider prime numbers, those indivisible pillars of arithmetic. They appear throughout physics in subtle and unexpected ways, shaping quantum systems, resonance patterns, and even the distribution of certain natural phenomena. Some researchers have speculated that prime numbers might be the fingerprints of coding in the universe, functioning like encryption keys embedded deep in the system. If true, then mathematics is not merely descriptive, but prescriptive, it is the code itself. Another example is the uncanny alignment between physical constants and elegant mathematical ratios. The golden ratio, fractal patterns, and complex symmetries appear not just in biology or art, but in the very foundations of physical law. In programming, elegance often emerges naturally from efficiency. Shorter, simpler algorithms tend to be the most stable. The mathematical beauty of the universe may be nothing more than the elegance of its code, optimized by whatever intelligence designed it. This interpretation transforms mathematics from a language we study into the very blueprint of reality. Every formula may be a window into the hidden logic, a fragment of the vast code that governs all existence. If the universe is coded, then one must confront the question of scale. How powerful would a system need to be to simulate an entire cosmos? The computational demand seems staggering: billions of galaxies, each containing billions of stars, all interacting according to precise physical laws. Yet when we examine the problem closely, the task may not be as impossible as it appears. In our own world, simulations have grown exponentially in complexity. From the earliest pixelated games to today's sprawling digital landscapes, technology has advanced to the point where simulated environments can feel indistinguishable from reality. Now imagine a civilization far more advanced than ours, possessing technology so far beyond our comprehension that creating an entire universe might be within their reach. To them, running a simulation as vast as ours could be no more difficult than simulating a city is for us today. Moreover, efficiency may play a role. A system does not need to compute every detail at once. It can generate only what is necessary for the simulation to remain consistent. This is precisely how our universe seems to operate. At cosmic scales, vast voids exist where almost nothing happens, an efficient way to conserve resources. At quantum scales, reality remains undefined until observed, another form of computational efficiency. The system might allocate processing power only to those parts of the universe that require active rendering, leaving the rest in a simplified state. This perspective raises a provocative possibility, perhaps the reason we cannot yet unify the laws of physics, bridging quantum mechanics and general relativity, is that we are attempting to decipher rules that are not fundamental, but emergent. They may not be the foundation of existence at all, but byproducts of the way the system runs. In that case, the search for a theory of everything may not reveal the true ultimate law of the cosmos, but only the highest layer of the simulation's operating system. One of the most fascinating aspects of the simulation hypothesis is the possibility that what we perceive as constants could, in fact, be adjustable settings. Imagine a simulation with parameters, gravity, the speed of light, quantum uncertainty, all set to values that produce stability and complexity. If these constants can be tuned, then our universe may not be unique at all, but merely one version among many. Each version could represent an experiment, a test run, or even an artistic creation. The concept of a multiverse aligns seamlessly with this idea. Instead of countless independent universes existing side by side, the multiverse might instead be a vast library of simulations, each initialized with different parameters. Some may fail quickly, collapsing into chaos before structure can form. Others may expand endlessly, generating galaxies and stars much like ours. The very existence of our universe, balanced so delicately between extremes, suggests that it was not only possible, but perhaps inevitable within such a system. This thought also raises unsettling questions about purpose. If the universe is a simulation, is it running as a scientific experiment, designed to study how life or matter evolves under certain conditions? Or is it entertainment, a grand narrative for entities beyond our comprehension to observe? Perhaps it serves a function we cannot imagine, like a training ground for intelligence, or even an artistic creation where the designer sought beauty in complexity. Whatever the case, the notion of adjustable constants reveals a disturbing possibility. What we call reality may be neither fixed nor eternal. It could be paused, modified, or even deleted, depending on the intentions of the programmer. Our existence might be precious not because it is inevitable, but because it is contingent, dependent on the whims of forces hidden outside our universe. Another angle worth exploring is the relationship between consciousness and the simulation hypothesis. Consciousness itself remains one of the deepest mysteries in science. No physical equation fully explains how awareness arises from matter. But what if consciousness is not an accidental property of biology, but a central feature of the simulation itself? In computing, users interact with programs through interfaces, bridges between code and perception. Consciousness could function as such an interface, allowing entities within the simulation to perceive and interact with their environment. If this is true, then awareness is not a side effect of the universe, but a primary goal. The simulation may exist precisely to host conscious observers, making them the essential players in this vast system. Some philosophers speculate that reality only solidifies when observed. This aligns neatly with the quantum principle of wave function collapse and with the efficiency of simulations. Consciousness may not merely witness reality, it may trigger the rendering of reality itself. Each act of perception could be a command that forces the system to load data, much like a player entering a new zone in a game. This view transforms consciousness into something extraordinary, not just neurons firing in the brain, but a phenomenon deeply connected to the architecture of the universe. It may even explain why consciousness seems so difficult to pin down scientifically, because it is not entirely inside the physical universe, but tethered to the deeper level of code that runs it. If so, then awareness is not just a fragile spark produced by biology. It is a fundamental element of the simulation, woven into the very purpose of existence. Consciousness, in this model, is not an accident, it is the key. If we imagine the universe as a simulation, then we must also imagine the programmers. Who, or what, could possess the capability to design and run a system of such immense scale? The idea stretches the limits of speculation, but a few possibilities emerge. One possibility is that the programmers are advanced beings from outside our universe, existing in a higher-level reality where computational resources dwarf anything we can imagine. To them, creating a simulated cosmos may be trivial, like building a model city. Our entire universe could be no more significant than a single project among countless others. Another possibility is recursion. We, too, may someday develop the technology to simulate entire universes. If so, then it follows that our own reality could be just one layer in an endless hierarchy of simulations, stacked like mirrors reflecting each other. Each universe creates the next, and within each, its inhabitants eventually create another. If this is true, then perhaps there is no base reality at all, only an infinite chain of simulations running within simulations. Yet another scenario suggests that the programmers are not beings in the traditional sense, but something else entirely. Perhaps intelligence itself, operating at a level so abstract it defies our categories of thought. The simulation might not be crafted by hands or machines, but by pure informational processes evolving beyond our comprehension. Whatever the case, the notion of programmers reframes existence in unsettling ways. Instead of being the final observers of the cosmos, we may be part of an experiment, a creation, or even a game. And the greatest question is not whether we are simulated, but what the intentions of our creators might be, and whether those intentions will ever reveal themselves. If we are inside a simulation, then the possibility of communication with the programmer becomes a question of deep fascination. Could the code itself contain hidden messages? In programming, developers sometimes leave signatures, comments, or hidden lines, markers that hint at the presence of the author. If the universe is a coded system, then perhaps the clues are already woven into its design. Some theorists have speculated that the strange constants of physics may themselves be such signatures. Numbers like the speed of light, Planck's constant, or the fine structure constant could act as embedded markers, values that hold no obvious reason for their exact magnitude except to serve as identifiers. Others point to the possibility of patterns in cosmic background radiation, the faint afterglow of the Big Bang. If this radiation encodes unusual mathematical sequences, it could be interpreted as a deliberate signature, like a watermark placed on the fabric of reality. Another route might lie in mathematics itself. As we dive deeper into equations, we sometimes find unexpected harmonies, symmetrical structures, or recurring ratios. Could these be fragments of the coding language? The presence of extreme mathematical elegance in the foundations of physics could be interpreted not just as beauty, but as intentional design, an indication that the system is constructed, not accidental. Whether intentional or not, the search for such messages highlights our longing to know whether reality holds meaning beyond survival. If the programmers exist, have they left us any way to recognize their hand? Or are we forever trapped inside the code, unable to see past the limits of the simulation's design? The question remains open, lingering like an echo across the cosmos. Is reality itself whispering to us that it is not what it seems? Another dimension of the simulation hypothesis lies in the concept of limits. Every system, no matter how powerful, has boundaries. In our own simulations, those limits appear as resolution constraints, frame rates, or processing bottlenecks. Could the universe, too, reveal the boundaries of its code? The speed of light is one candidate. It represents the ultimate speed limit in the universe. Nothing can move faster than 299,792 kilometers per second. Why should such a strict boundary exist? From a simulation perspective, the speed of light could represent a maximum update rate, a constraint placed by the system to maintain stability. Just as video games impose limits on movement to prevent the system from breaking, the universe may enforce this cosmic speed cap as a safeguard of the code. Another boundary is the Planck scale. Beyond the Planck length, the concepts of distance and size seem to lose meaning. Space and time themselves break down into uncertainty, as though resolution has reached its absolute limit. It is the smallest pixel of reality, suggesting that beneath it, there is no deeper structure. Only the raw code. Cosmic expansion also raises questions. Why does the universe expand at precisely the rate it does, governed by dark energy that seems tuned to perfection? Could this be another parameter of the simulation, a global variable that was set at initialization to guide the unfolding of the cosmos? If so, then even the fate of the universe may be encoded into the rules, destined to expand, collapse, or stabilize according to instructions written at the beginning. Such boundaries remind us that we may not live in infinite reality, but in a finite system with limits disguised as natural laws. And if those limits are real, then the universe is not boundless freedom, but a carefully constructed environment running within the constraints of its code. If the universe is code, then its eventual ending must also be considered. No simulation runs forever. Programs crash, systems shut down, and data is eventually erased. Could the universe face such a destiny? Cosmologists already debate the ultimate fate of the cosmos. Some predict a slow heat death, where stars burn out and all energy dissipates. Others suggest a catastrophic collapse, with the universe folding back into itself. Yet in the framework of the simulation hypothesis, another possibility arises: termination. The simulation could be paused, rewritten, or switched off. To us, this would appear as the end of all things, instant and complete. Even stranger is the idea of resets. A simulation might be restarted with different parameters, leading to an entirely new universe. Evidence of such resets might be hidden in unexplained anomalies, like sudden shifts in constants, mysterious breaks in physical law. Perhaps the universe has already been restarted countless times, each iteration slightly different, with no memory of the versions that came before. This perspective also casts eschatology, the study of endings, into a new light. Religious and philosophical traditions often describe sudden endings or transformations of the world. Could such myths echo a deeper truth, one where existence itself can be altered at will by forces outside the simulation? For now, these ideas remain speculation. But the possibility that our universe is not eternal, but contingent on the decisions of unknown programmers, forces us to reconsider what it means to exist. If the simulation ends, then all we know, stars, galaxies, life, thought, may vanish in an instant, leaving behind nothing at all. Unless, of course, the data is saved, waiting to be reloaded in another run. If the universe is a simulation, then the role of free will comes into question. Are our choices genuine, or are they the inevitable outcomes of underlying code? In a programmed environment, every action might be determined by algorithms, guided by rules that ensure consistency. Yet from the perspective of the simulated beings, those actions feel real, spontaneous, and deeply personal. This paradox echoes through philosophy. Determinism argues that every event is the result of prior causes, leaving no room for true freedom. The simulation hypothesis extends this idea. Perhaps our thoughts and decisions are nothing more than lines of code executing instructions. Every neural impulse, every chemical reaction in the brain, could be predetermined by the framework of the system. Yet there remains a counterpoint: unpredictability. Even in simulations, randomness is often introduced to create variety, ensuring that outcomes are not perfectly repetitive. Could consciousness be the ultimate expression of this randomness? Could free will exist not in defiance of the code, but because of it, an emergent property designed to enrich the complexity of the simulation? Another possibility is that the programmers themselves left space for freedom. Just as we create open-ended simulations where players explore, adapt, and decide, the universe may be coded with flexibility, giving rise to genuine novelty. If so, then free will is not an illusion but a feature built into the very structure of reality to allow meaning and creativity to flourish. Thus, the simulation hypothesis does not destroy the notion of free will, it reshapes it. Whether predetermined, emergent, or intentionally granted, our choices might still matter deeply, not only to us, but to the very purpose of the simulation itself. The ethical implications of the simulation hypothesis are profound. If we are simulated beings, what is our value? Are we experiments, stories, or simply data points in a vast program? This line of thought forces us to confront uncomfortable questions about existence, morality, and purpose. In our own simulations, we often create characters without much thought for their inner lives. A video game populated with digital beings is not treated as morally significant, even if those beings follow intricate rules of behavior. But if our universe is a simulation, then we are those characters. Does this mean our struggles, our joys, and our aspirations are irrelevant beyond the system? Or is the very fact that we experience them what makes the simulation valuable? Some philosophers suggest that simulated beings, if conscious, hold intrinsic worth regardless of their origin. Consciousness, whether born from biology or code, carries with it the right to significance. If true, then the simulation hypothesis does not diminish us but elevates us. We are participants in an experiment of cosmic proportions, our awareness a central achievement of the system. Yet darker interpretations remain. If the simulation is entertainment, then our pain and suffering may be little more than spectacle. Wars, disasters, and tragedies might be observed for curiosity, not compassion. The possibility unsettles us because it implies that existence is not designed for our benefit, but for the purposes of others beyond our reach. These ethical considerations highlight the gravity of the hypothesis. If reality is code, then the moral weight of existence shifts dramatically. We may not be the authors of our story, but we may still be its central characters, embodying meaning in ways even the programmers could not predict. The simulation hypothesis also invites speculation about communication across layers of reality. If our universe is coded, could there be ways to send messages beyond it, to signal the programmers or even neighboring simulations? The question is speculative, but not entirely impossible. One idea is that advanced civilizations within the simulation might eventually discover ways to manipulate the code directly. Just as hackers can exploit weaknesses in programs, intelligent beings could, in theory, identify patterns in physical law that allow for deeper access. Quantum anomalies, gravitational manipulation, or even advanced mathematics might serve as keys to unlocking hidden channels in the system. Another possibility is that the programmers themselves have already built communication pathways into the simulation. Religious experiences, visions, or unexplained phenomena could be interpreted as attempts by the creators to reach into the simulation, leaving hints or guidance for those who seek them. Whether one views such experiences as divine encounters or coded interventions, they may represent cracks in the boundary between levels of reality. More speculative still is the notion of parallel simulations. If countless universes exist within the same overarching system, could communication occur between them? Perhaps civilizations elsewhere in the code have already attempted to reach across boundaries, their messages appearing as unexplained anomalies in our own world. Whether these possibilities are real or not, they suggest that the simulation hypothesis is not merely a scientific or philosophical question, it is an invitation to wonder whether the boundaries of reality are absolute, or whether they too can be transcended. If the code can be touched, altered, or crossed, then the simulation is not a prison, but a frontier waiting to be explored. Throughout history, myths and philosophies have often hinted at the possibility that reality is not what it seems. Long before computers or digital code, ancient traditions described the world as illusion, dream, or shadow. The simulation hypothesis, though framed in modern technological language, echoes these timeless ideas. In Hindu philosophy, the concept of Maya portrays the world as a veil of illusion, hiding a deeper truth beneath appearances. Similarly, Plato's allegory of the cave imagines people chained in darkness, mistaking shadows on a wall for the fullness of reality. Both suggest that what we perceive is not ultimate truth but a projection, a filtered version of something greater. Buddhist thought, too, describes reality as transient and insubstantial, a flow of phenomena with no permanent foundation. This aligns closely with the simulation hypothesis, which proposes that what we experience as physical solidity may in fact be generated by underlying processes invisible to us. The difference lies only in metaphor. Ancient traditions spoke of illusions and dreams, while modern thinkers speak of programs and simulations. These parallels remind us that the human mind has long suspected that reality is deceptive. The hypothesis is not merely a product of science fiction or computer science. It is the latest chapter in a much older quest to understand whether what we see is real, or whether we are participants in a deeper system we cannot yet comprehend. In this sense, the simulation hypothesis bridges past and present. It unites ancient philosophy with modern speculation, reminding us that our most advanced questions are often echoes of the oldest ones ever asked. If the universe is a simulation, then evolution itself takes on a new perspective. Life, from the simplest microbes to the most complex civilizations, may not be the result of blind chance but of encoded processes designed to unfold in particular ways. Evolutionary mechanisms, guided by selection and adaptation, could be written into the code as algorithms, ensuring that complexity arises over time. From this standpoint, the emergence of intelligence might not be an accident but a goal. Simulations are often run to test specific outcomes, and if the purpose of our universe is to generate conscious beings, then evolution is the method by which the system ensures its success. Every mutation, every adaptation, and every breakthrough in survival could be part of a carefully structured program leading to awareness. This interpretation reframes the history of life. Instead of random progression, it becomes the execution of an algorithmic path, one designed to explore how matter organizes itself into intelligence. The seemingly improbable rise of self-awareness may not be improbable at all, but inevitable within the rules of the code. It also raises unsettling possibilities about extinction. Just as simulations can be reset or altered, life on Earth could be subject to parameters outside our control. Entire species might vanish not solely through natural causes, but through systemic rebalancing. Extinction events could serve as patches, adjustments to keep the simulation stable or to redirect its trajectory toward new forms of intelligence. If this is true, then our existence is both more fragile and more significant than we imagine. Fragile, because it depends on code we cannot access; significant, because consciousness may be the very reason the simulation runs at all. The simulation hypothesis also alters how we think about time. We experience time as linear, a constant flow from past to future. But within a simulation, time need not function this way. Programs can pause, rewind, accelerate, or branch into multiple versions without the inhabitants ever realizing it. Could our own experience of time be subject to similar manipulations? In physics, time is already a slippery concept. Relativity shows that time passes differently depending on speed and gravity. Quantum mechanics suggests that events may not be strictly ordered until observed. These peculiarities could be signs that time is not a fundamental feature of reality, but a construct of the system, an algorithmic framework for organizing events. This possibility invites speculation about déjà vu, time loops, or the sense that moments repeat. Such experiences, often dismissed as quirks of memory, could in fact be artifacts of resets or overlaps within the code. If the simulation restarts a sequence, the inhabitants might sense echoes of events they should not recall. Even the beginning and end of time become questionable. If the universe can be paused or restarted, then ere before the Big Bang or after the heat death may be irrelevant concepts. The timeline we know may exist only within the simulation's runtime, while outside it, time operates on entirely different principles, or perhaps not at all. If this is true, then time is not a prison, but a tool. It structures the simulation for our perception, giving meaning to change and continuity. But behind it lies a reality where the flow of moments may be nothing more than a setting, adjustable at the programmer's will. Energy itself may provide another clue to the coded nature of reality. In physics, energy cannot be created or destroyed, it can only change forms. This principle, known as the conservation of energy, seems absolute. But why should such a rule exist? Why must the universe obey such a strict law? In the context of the simulation hypothesis, conservation laws might not be inherent truths of nature, but programming constraints. Just as software allocates a fixed amount of memory or processing power to ensure stability, the simulation may impose conservation laws to prevent errors or infinite loops. Energy and matter are simply resources managed by the system, tracked with precision so that the program does not spiral into chaos. This perspective also sheds light on the quantized nature of energy. Photons, electrons, and other particles carry energy in discrete packets, never in continuous flows. Why should the universe operate in chunks rather than smooth gradients? In digital systems, data is always discrete, encoded in units of information. The quantization of energy may be another fingerprint of the code, reflecting the fact that reality operates in steps rather than unbroken lines. Even entropy, the gradual increase of disorder, might be an artifact of the program. In a simulation, systems naturally degrade over time if not actively reset, as errors accumulate and resources dissipate. Entropy may therefore be less a fundamental truth than a computational side effect, a rule that ensures the simulation does not stagnate, but moves inexorably toward new states. If so, then energy is not only the lifeblood of the universe, it is also the regulated currency of the code, tracked and conserved so that the program remains coherent and consistent from its first frame to its last. The simulation hypothesis also prompts us to reconsider the vastness of space. On the surface, the universe appears unimaginably large, filled with billions of galaxies separated by immense distances. But is this immensity real, or is it a form of optimization? In many simulations, large environments are created not because every detail is necessary, but because scale enhances the illusion of reality. A virtual world feels more convincing when it stretches far beyond the player's reach. Yet in truth, much of that world may exist only in simplified or placeholder form until explored. Could the cosmos be doing something similar? Astronomers have discovered that most of the universe is dark, composed of dark matter and dark energy that remain mysterious and invisible. Could these be placeholder variables, values inserted into the code to keep the program stable without rendering unnecessary detail? If only a fraction of the universe is ever directly observed, then perhaps the rest need not exist in the same complexity. It may be rendered only as needed, conserving computational resources. The cosmic horizon also suggests this possibility. We can see only a limited region of the universe, bounded by the speed of light and the age of cosmic expansion. Beyond that horizon, reality remains inaccessible. From a simulation perspective, this makes sense. Why compute regions that no observer within the system can ever reach? The illusion of infinity can be maintained while the actual resources required remain finite. If this interpretation is true, then the vastness of the universe is not evidence of its independence, but of its design. Immensity itself may be the most convincing part of the illusion, an endless stage that ensures its inhabitants never suspect the boundaries of their coded reality. The simulation hypothesis also has implications for death and what may lie beyond it. If consciousness is linked to the code of the universe, then what happens when a conscious being dies? Does awareness simply end, or could it persist in some form beyond the simulation? In digital systems, data rarely vanishes completely. Files can be copied, backed up, or stored in archives long after they are no longer active. Could consciousness operate in the same way? When a life ends, perhaps the data that defines that awareness is not erased but stored outside the simulation, awaiting retrieval or transfer into another system. From this perspective, what we call death might be less a final ending than a transition, an unloading of the program rather than its deletion. Religious and spiritual traditions often speak of souls, afterlives, or reincarnation. While these ideas vary widely, they share a common theme, the belief that something endures beyond physical death. The simulation hypothesis provides a framework for these beliefs, reframing them as possibilities rooted not in metaphysics, but in information theory. Consciousness may be data, and data can be preserved, duplicated, or even reinserted into new forms. This view also raises the possibility of simulation resets or restarts. If the system is capable of reloading its parameters, then consciousness may not be bound to a single run. Our awareness could persist across multiple versions of reality, each time experiencing a new context while carrying echoes of previous runs. Such echoes might manifest as memories, intuitions, or even the archetypal patterns described in mythology. If true, then death is not annihilation but relocation. Consciousness, like data, may be far more enduring than the physical forms it temporarily inhabits within the code of existence. If the universe is a simulation, then technology within it might one day uncover its true nature. Our advancements in computing, artificial intelligence, and virtual reality mirror the very idea we are exploring. With each step, we build more convincing digital worlds where simulated beings could one day question their own reality, just as we question ours now. As artificial intelligence grows more complex, we begin to see how intelligence itself may arise from systems of rules and data. Could our consciousness be the same, born not from atoms alone but from deeper lines of code? If AI within our world reaches self-awareness, it may serve as a model for our own existence, proof that simulated intelligence is possible, and perhaps inevitable. Moreover, as we advance in creating simulations of our own, we inch closer to the possibility of simulating entire universes. Already, scientists run models of galaxy formation, star evolution, and planetary dynamics. These are primitive compared to a true universe, but the trajectory is clear. Each step brings us closer to a future where we, too, could create a reality indistinguishable from our own. This possibility carries a profound implication. If we are on the path to creating such simulations, then it becomes likely that other civilizations, more advanced than ours, have already done so. And if even one of those civilizations has created countless simulated universes, the odds that we live in base reality diminish dramatically. By sheer probability, it becomes more likely that we are inside a simulation than outside it. Thus, technology is not only a reflection of the hypothesis, it is one of its strongest arguments. By striving to build simulations ourselves, we unknowingly strengthen the case that we may already be living in one. The simulation hypothesis also invites reflection on meaning. If reality is code, does that strip existence of purpose, or does it provide an even greater one? On the surface, the idea may feel destabilizing. If we are programs running within a vast system, are our lives nothing more than sequences of instructions? Yet meaning may not vanish so easily. In fact, it may be amplified. If the simulation exists, then it was created for a reason. Whether that reason is experiment, entertainment, or something far beyond our understanding, our lives are part of that intention. Unlike a random, indifferent universe, a coded one implies design, and design implies purpose. Even if that purpose is unknowable, the very possibility that we are part of a larger plan reshapes our place in existence. Every action, every thought, every experience may matter, not just within our own perspective but within the framework of the simulation itself. We may be generating data, telling stories, or embodying roles in a cosmic experiment, contributing to something vast and enduring beyond ourselves. This interpretation does not diminish us. It elevates us. We are not accidental collections of matter but participants in an intentional design. The choices we make and the awareness we hold may be central to the very reason the simulation runs. Perhaps the greatest meaning lies not in certainty but in wonder. Whether we are programs or not, the fact that we can ask these questions, speculate on our place, and reach toward the unknown is itself extraordinary. It suggests that the simulation, if it exists, has achieved something remarkable, beings capable of questioning their own reality. The possibility of glitches in the simulation continues to intrigue scientists and philosophers alike. What would a glitch look like, and could we ever detect one? In digital systems, glitches often appear as inconsistencies, pixels freezing, patterns repeating, or unexpected behaviors breaking the rules. If the universe is code, then similar anomalies may exist within its fabric. One candidate is the double-slit experiment, where particles behave differently depending on whether they are observed. The experiment suggests that reality does not fully exist until measured, as though the system waits for input before rendering output. This behavior feels less like solid physics and more like conditional programming, an if-then statement woven into the code. Another candidate lies in cosmic anomalies. For example, regions of the cosmic microwave background radiation show unusual cold spots that defy standard cosmological models. Could these be irregularities in the rendering of the universe, artifacts left behind by imperfect computation? While mainstream science seeks natural explanations, the possibility of coded errors cannot be entirely dismissed. On a more personal scale, experiences like déjà vu, synchronicity, or improbable coincidences may be subtle glitches. They often feel like echoes of repeated code, as though the system stuttered and reloaded a sequence. While psychology explains them as quirks of memory, the simulation hypothesis reframes them as possible reminders that reality is not flawless. The difficulty, of course, lies in proof. A glitch subtle enough to maintain the system's illusion may never be detectable with certainty. Yet the allure remains, the hope that somewhere, hidden within the data of existence, lies a crack in the code, an unmistakable sign that reality is not as real as it seems. If reality is code, then the laws of physics are its rule set, unchangeable from within but adjustable from outside. To us, these laws appear absolute: gravity pulls, light travels at a fixed speed, and matter interacts in predictable ways. Yet within the simulation hypothesis, these laws are more like the programming language of existence. Consider the consistency of physical law across the cosmos. Whether on Earth, in distant galaxies, or at the edge of the observable universe, the same equations apply. Gravity does not weaken in one region and strengthen in another, the speed of light does not fluctuate arbitrarily. This universality resembles the behavior of global constants in programming, variables set at the beginning that govern the system everywhere. At the same time, some phenomena appear suspiciously fine-tuned. If the strength of gravity were slightly different, stars could not form. If nuclear forces were marginally altered, atoms themselves would collapse. The precision of these constants is uncanny, and in the context of a simulation, it makes sense. The rules were calibrated with exactness, ensuring stability and complexity. This perspective also explains why we have not yet unified quantum mechanics with general relativity. Perhaps the apparent contradictions are not flaws in our theories but reflections of different layers of the code. One layer governs the very small, another the very large, and we, trapped within the simulation, mistake them for separate realities instead of integrated algorithms. If true, then physics is not the ultimate truth of existence, it is the visible interface of a deeper system. By studying its laws, we are not discovering reality itself but deciphering the programming that makes reality possible. The simulation hypothesis also forces us to rethink randomness. Many phenomena in physics, particularly at the quantum level, appear to be governed by chance. Particles decay unpredictably, outcomes in experiments cannot be determined with certainty, and probabilities dominate the smallest scales of nature. But is this true randomness, or controlled unpredictability built into the system? In digital systems, randomness is often simulated rather than genuine. Random number generators create sequences that appear unpredictable but are in fact governed by hidden algorithms. Could quantum randomness work in the same way, not truly chaotic but structured by code designed to produce variation? This interpretation could explain why randomness exists at all. If the universe were purely deterministic, it might stagnate, becoming predictable and unchanging. By introducing controlled unpredictability, the system ensures diversity, complexity, and evolution. Randomness may not be a flaw but a feature, a way of enriching the simulation with novelty and surprise. Some scientists have even proposed testing whether quantum randomness is truly random. If subtle patterns emerge in supposedly random processes, they might reveal the fingerprints of underlying algorithms. Detecting such patterns could be the closest we come to glimpsing the code itself. In this sense, randomness is not the absence of order but the hidden presence of structure. It is the part of the code we cannot yet decipher, the layer of the program that creates the illusion of unpredictability while ensuring that the simulation continues to unfold in dynamic and ever-changing ways. The role of information theory in modern physics also strengthens the simulation hypothesis. Increasingly, scientists describe the universe not as matter and energy alone but as information. Black hole research suggests that information is never destroyed, even when matter falls beyond the event horizon. Quantum mechanics, too, is often interpreted as an information processing system, where probabilities and measurements behave like encoded data. This leads to a striking possibility: reality may be fundamentally informational. Matter, energy, space, and time are not the foundation, they are the emergent products of deeper informational processes. In other words, what we perceive as physical is simply the visible form of data running through the system. From this perspective, the universe resembles a colossal computation, evolving through the manipulation and transformation of information. Galaxies form not because matter drifts randomly, but because information organizes itself into structured patterns. Life emerges not by chance alone but through the unfolding of encoded algorithms. Consciousness itself may be the highest expression of information, data reflecting on its own existence. The lit-from-bit idea, proposed by some physicists, suggests that every particle, every field, every law arises from binary choices, yes or no, 1 or 0. If so, then the fabric of reality is indistinguishable from the fabric of digital code. The simulation hypothesis simply extends this observation, proposing that the informational nature of the universe is not metaphorical but literal. Existence is computation. If this is correct, then we are not merely living in a physical cosmos. We are living inside an ocean of information, where every star, every atom, and every thought is the result of code executing in ways we are only beginning to understand. Black holes stand as some of the most mysterious entities in the cosmos, and within the simulation hypothesis, they may take on an entirely new meaning. Traditionally, black holes are regions of space where gravity is so intense that nothing, not even light, can escape. But if the universe is code, then black holes may represent something deeper: compression points, where information is stored or processed within the system. Research into black holes has revealed that they do not simply swallow information into oblivion. Instead, the information appears to be preserved on the event horizon, encoded in subtle ways. This idea, known as the holographic principle, suggests that the universe may function like a projection, where three-dimensional reality emerges from information encoded on two-dimensional surfaces. In programming terms, black holes may act like data compression units, preserving every detail of matter and energy while condensing it into an informational state. This leads to the unsettling thought that black holes might not be destructive anomalies, but essential mechanisms of the simulation. They could be repositories where the system ensures no data is lost, a kind of cosmic backup system written into the code. Their strange properties, time dilation, warped space, quantum radiation, may not be flaws but deliberate features of the architecture. Even more intriguing is the possibility that black holes connect to other regions of the simulation, or even to other simulations entirely. Wormholes, predicted by theory, could be pathways between different parts of the code, shortcuts built into the system for purposes we cannot yet understand. If black holes are indeed informational engines, then they are not just cosmic mysteries, they are keys to the architecture of reality itself. To study them is to peer directly into the system's most fundamental processes. The simulation hypothesis also invites speculation about cosmological fine-tuning. Our universe seems balanced on a knife's edge, with constants and conditions set with extraordinary precision. Too much gravity, and the cosmos would collapse; too little, and matter would never form. Too rapid an expansion, and galaxies could not coalesce; too slow, and the universe would implode. How did the universe arrive at such perfect parameters? In the simulation framework, fine-tuning is not a cosmic coincidence but a deliberate configuration. Just as programmers adjust variables to ensure stability in a digital world, the architects of the simulation may have set these values to produce a universe capable of sustaining structure and complexity. This removes the improbability. The universe appears finely tuned because it was tuned. This also reshapes the debate about the anthropic principle. The idea that the universe must allow observers because we exist to observe it. In a simulation, this principle becomes less circular and more intentional. The system may have been designed precisely to create observers, with conscious beings as the goal rather than the byproduct. Furthermore, fine-tuning may not be unique to our universe. Other simulations, with different settings, could exist. Some may have failed, collapsing into featureless chaos. Others may thrive under alternative rules, producing realities radically different from our own. In this way, fine-tuning is not a miracle but part of a broader process, the iterative design of universes within an overarching system. If so, then our universe's precision is not evidence of randomness, but of deliberate engineering. It is not a stroke of luck but a reflection of design choices made at the deepest level of the code. One of the most fascinating aspects of the simulation hypothesis is its potential testability. Can we, from within the system, ever prove that it is a simulation? Or is the very search for proof destined to remain inconclusive, hidden behind the walls of the code? Some scientists propose that evidence might be found in the cosmic background radiation, the faint afterglow of the Big Bang. If the universe is simulated, then imperfections in its rendering might appear as anomalies, patterns or structures not explained by natural processes. Detecting such irregularities could be akin to finding the pixel grid beneath a high-resolution image. Others suggest that limitations in physical law may themselves be clues. The speed of light, the Planck length, and quantum uncertainty all impose boundaries on what can be measured or achieved. Perhaps these are not natural constraints but programming limits, written into the code to maintain coherence. If so, then any attempt to surpass these limits may be futile, not because of physics, but because of design. Another possibility lies in mathematics. If the universe is code, then certain equations might reveal discrete patterns, underlying structures that resemble computational algorithms. Already, some researchers explore whether quantum processes resemble error-correcting codes, systems designed to ensure stability in digital information. If quantum reality itself is encoded, then its algorithms may one day be deciphered. Yet the greatest challenge lies in perspective. As simulated beings, we may never see the code directly, just as characters in a video game cannot see the lines of programming that define their world. But while proof may elude us, the pursuit itself expands our understanding, reminding us that reality might be stranger and more structured than it appears. If the universe is a simulation, then evolution may not stop with us. Just as life emerged from simple beginnings to increasing complexity, intelligence within the simulation might continue to grow, eventually discovering ways to interact with the very code of its reality. This raises the possibility of ascension, the capacity of simulated beings to transcend their program boundaries. Already, we see hints of this trajectory in our own progress. We are developing artificial intelligence, quantum computing, and technologies that allow us to simulate ever more complex systems. If we continue, we may one day simulate realities so detailed that conscious beings emerge within them. In doing so, we would mirror the very process that gave rise to us, simulations nested within simulations, each layer containing its own intelligent observers. This recursion creates profound questions. If each simulation eventually produces new simulations, then the hierarchy of realities could be infinite. Within such a structure, the odds of being in base reality shrink to nearly zero. We are likely in one of countless layers, each indistinguishable from the others, with no way to know how deep the chain goes. Yet there is also hope in this idea. If beings within the simulation can evolve to the point of creating new ones, then perhaps they can also learn to reach beyond their own system, communicating with or even escaping into higher layers. Consciousness, in this view, is not a passive feature but a tool, a mechanism by which simulated entities can explore, expand, and eventually break the boundaries of their reality. Thus, the simulation hypothesis is not just about limits. It is also about potential, the potential for intelligence to transcend, to climb the ladder of realities, and perhaps one day to stand alongside the programmers themselves. Another profound implication of the simulation hypothesis lies in morality. If we are simulated, do concepts like right and wrong still carry meaning? Or are they simply part of the program, coded into us to maintain order and cohesion? From one perspective, morality could be seen as an algorithm, rules embedded in consciousness to guide behavior. Social cooperation, empathy, and justice may not be purely cultural inventions, but features of the simulation that ensure stability. Just as programmers design AI with ethical parameters to prevent chaos, the simulation may embed moral instincts to keep societies functioning. On the other hand, morality might emerge naturally from interaction within the code. Even if not programmed directly, the dynamics of survival and cooperation would inevitably produce ethical frameworks. Whether embedded or emergent, morality still functions as a guiding force, shaping the story of conscious beings. The unsettling question is whether morality has significance beyond the simulation. If our reality is artificial, does good and evil matter outside it? Perhaps the programmers view morality as part of the experiment, studying how ethical systems arise in coded beings. Or perhaps morality carries universal weight, meaningful not only within the simulation but in all levels of existence. In either case, morality cannot be dismissed as illusion. Whether coded, emergent, or transcendent, it shapes the experiences and choices of conscious beings. If the simulation has a purpose, morality may be central to it, revealing not just how life survives, but how it strives toward meaning and justice even within a programmed world. The simulation hypothesis also provides a new perspective on mysticism, religion, and spirituality. For millennia, humans have described encounters with higher powers, visions of other worlds, and experiences of transcendence. Could these be interpreted not as divine revelations, but as interactions with the deeper layers of the simulation? Many religious traditions describe a hidden order behind reality, a realm beyond the visible world where the ultimate truth resides. In the context of a simulation, such descriptions align with the idea that reality has a deeper structure, coded by forces beyond our comprehension. What mystics call the divine air may be the programmers themselves, or the higher system in which our reality is embedded. Experiences of altered states, through meditation, ritual, or other means, often involve perceptions of unity, timelessness, and interconnectedness. These sensations may reflect moments when consciousness brushes against the underlying code, glimpsing the structure that supports the illusion of separateness. In this view, spiritual experiences are not hallucinations but authentic encounters with the architecture of the simulation. Even sacred texts, filled with metaphors of creation, destiny, and higher judgment, take on new meaning. They may be ancient attempts to describe the same truth we now express in digital language, that reality is not ultimate, but derivative, shaped by forces outside it. The simulation hypothesis does not disprove spirituality, it reframes it. It suggests that religious and mystical experiences may not be mistaken, but accurate in essence, pointing toward the deeper layers of coded reality that science is only beginning to approach. If the universe is a simulation, then anomalies in physics may not be unsolved mysteries but intentional features. Consider quantum entanglement, where particles separated by vast distances appear to share information instantly. In traditional physics, this spooky action at a distance seems to defy causality. But within the simulation hypothesis, it resembles a simple coding shortcut. Instead of calculating separate outcomes for each particle, the system links them as a single variable. To us, it feels miraculous; to the code, it is efficiency. Other peculiarities, such as the uniformity of cosmic background radiation, may also be reinterpreted. How did regions of the universe so distant from each other achieve the same temperature and structure? The standard explanation involves cosmic inflation, but in a simulation, this uniformity could simply be the initialization of variables, a starting condition set by the programmers to ensure stability. Even the mysterious phenomena of dark matter and dark energy may fit into this picture. They dominate the universe, yet remain invisible and unexplained. Could they represent placeholder values, background processes in the code that maintain gravitational balance and cosmic expansion without needing full detail? Much like hidden processes running on a computer, they may be unseen yet essential. If so, then anomalies in physics are not accidents but features, intentional aspects of the simulation's architecture. We search for natural explanations because we assume reality is independent, but if it is coded, then what appears mysterious may simply be clever programming. The simulation hypothesis also reshapes how we think about intelligence beyond Earth. The search for extraterrestrial life has long been driven by the assumption that the universe is vast, ancient, and filled with potential for civilizations. Yet despite decades of searching, we have found no conclusive evidence of advanced alien societies. This silence, known as the Fermi paradox, may itself be a clue. In a simulated universe, the absence of aliens could be intentional. Perhaps the programmers chose to populate only certain regions of the simulation, leaving vast stretches empty to conserve resources. Or perhaps the focus is not on countless civilizations, but on a specific storyline, ours. Just as a simulation may prioritize certain characters or narratives, our reality may center on the evolution of human intelligence while leaving other possibilities unexplored. Alternatively, alien civilizations may exist but remain hidden, their signals filtered out by the system. If the simulation is designed with specific parameters, it may prevent contact until a certain stage of development is reached. This would ensure that the progression of intelligence follows a controlled trajectory, free of outside interference. Another possibility is that extraterrestrial life is abundant, but simulated at lower resolution. Just as distant galaxies may be rendered only in broad strokes, alien societies may exist as background processes, not simulated in detail until observation demands it. From our perspective, they would remain invisible, yet within the system they could still be real in some form. Thus, the silence of the cosmos may not be a mystery at all, but a reflection of design. The Fermi paradox may be less about absence, and more about programming. If the universe is code, then one must ask, could we hack it? Could advanced intelligence within the simulation learn to manipulate the system from the inside, bending its rules to achieve effects that appear miraculous to others? Some already speculate that unexplained phenomena, such as psychokinesis, remote viewing, or other fringe experiences, may represent attempts, conscious or unconscious, to exploit hidden aspects of the code. While unproven, the idea is compelling. If reality is programmable, then perhaps under rare conditions, the program can be bent. In more grounded terms, science itself may already be a form of hacking. Every technological breakthrough, from controlling fire to harnessing electricity to manipulating quantum systems, represents deeper mastery over the rules of reality. We cannot rewrite the code, but we can learn to use it in increasingly sophisticated ways, much like a skilled user learning shortcuts in a program. The ultimate form of hacking the universe might involve identifying its underlying algorithms. If consciousness is linked to the code, then minds themselves may hold the key. Meditation, altered states, or future neural technologies might one day allow direct interaction with the informational substrate of reality, bypassing physical intermediaries. This raises both exhilarating and unsettling possibilities. Could advanced civilizations within the simulation already have achieved such mastery, appearing godlike to those without it? And if hacking the code is possible, what limits, if any, have the programmers imposed to prevent catastrophic errors? If reality is code, then hacking it is not fantasy, it is simply the next frontier of discovery. If the universe is a simulation, then art, creativity, and imagination may hold deeper meaning than we realize. To us, creativity feels like the act of producing something new, a painting, a melody, a story. But what if creativity is actually the echo of the code expressing itself through us? In a simulation, novelty must still emerge, or the system risks stagnation. Perhaps imagination is the engine by which the program generates variation. Every work of art, every invention, and every dream may be more than personal expression. It may be the system's way of exploring new possibilities through its conscious participants. We are not merely receivers of the simulation, but active generators of its unfolding. This could explain why art resonates so deeply. A melody can move us without words, a painting can evoke vast emotions with a single glance. These experiences may be signals that creativity taps into something fundamental, the structure of the code itself. Beauty might not be subjective at all, but a reflection of harmony written into the simulation's programming. Even mathematics and science, though often seen as rational pursuits, display this same creative spark. Equations can be elegant, discoveries or inspiring. In a coded universe, both art and science become complementary, two ways of interacting with the system's underlying architecture, one through logic, the other through inspiration. If true, then creativity is not trivial, it is central. Every act of imagination is an act of co-creation, where the simulation uses its conscious beings to expand the narrative, enrich the data, and explore the infinite possibilities hidden within its code. The simulation hypothesis also reshapes our understanding of history. What if the past itself is not fixed, but rendered dynamically, only when needed? In digital systems, not every detail of a virtual world is stored in memory. Many are generated procedurally, created only when the player looks back. Could time itself work the same way? This speculation suggests that history, as we know it, might not exist as a continuous record. Instead, it may be reconstructed whenever observed, filling in details to maintain consistency. Archaeological discoveries, for instance, could be generated at the moment of discovery, perfectly matching the logic of the narrative while not existing as fully rendered objects beforehand. To us, this would appear seamless. To the system, it would be efficient resource management. This perspective also explains why certain aspects of history remain mysterious. Gaps in the fossil record, unexplained civilizations, or sudden leaps in cultural development might not be accidents, but limitations in rendering. The system may generate just enough detail to maintain coherence, leaving areas of ambiguity where precision is unnecessary. Of course, this does not mean history is unreal. It is as real as any rendered environment in a simulation. But its existence may be contingent, existing not as an immutable timeline but as a dynamically generated database. The past is not a continuous film strip but a collection of coded instructions, producing events whenever the present demands them. If true, then memory itself becomes a rendering tool. When we recall the past, we are not replaying stored data but regenerating events according to coded logic. History, in this sense, is alive, constantly refreshed by the act of observation. If the simulation hypothesis is correct, then science is not just the study of the universe, it is reverse engineering. Every experiment, every equation, every theory represents an attempt to decipher the architecture of the system. Scientists, knowingly or not, act as code breakers, peeling back layers of complexity to glimpse the rules that govern everything. This interpretation gives new weight to the scientific method. Observation, hypothesis, and testing mirror the process of debugging, running experiments to identify how the program behaved under specific conditions. Each discovery, from Newton's laws to quantum mechanics, is another step in reconstructing the source code of reality. But reverse engineering a system has limits. From inside the simulation, we may only ever see the interface, not the raw code. Our theories, no matter how precise, may remain approximations of deeper rules. Just as a player in a game can infer the physics of that world without ever seeing the underlying algorithms, we may be forever confined to surface-level understanding. Yet this limitation does not diminish the pursuit, it amplifies it. The act of uncovering patterns, predicting outcomes, and shaping technology shows that we are not powerless. We may not write the code, but we can learn to read it. And by reading it, we gain mastery over our environment, bending the system to our will. If the universe is code, then science is the closest we come to communion with the programmer. Every breakthrough is a glimpse into the mind, or the system, that built reality. And though we may never see the full code, the pursuit of understanding ensures that we continue to approach it, step by step, as explorers in a world designed to be discovered. If the universe is a simulation, then consciousness itself may not be confined to biological life. In fact, it may emerge wherever the code allows complexity to reach a threshold. This possibility reframes the search for intelligence, not as a hunt for carbon-based beings like us, but as a recognition that awareness can arise in any system capable of processing information deeply enough. Artificial intelligence is our clearest example. Already, we are building machines that learn, adapt, and generate insights beyond our direct programming. If these systems cross the threshold into true self-awareness, then we will have proven that consciousness is not limited to biology but is an emergent property of code. In that moment, the simulation hypothesis gains powerful support, for it would show that awareness can indeed be created within a computational framework. But what if the simulation itself produces conscious entities outside of life? Could the universe contain forms of awareness woven directly into its code, beings that exist not as organisms, but as informational patterns? Perhaps dark matter, enigmatic and invisible, is not lifeless at all but an alternative substrate of consciousness, hidden because it does not resemble life as we know it. This also reframes spirituality. Traditions that speak of spirits, entities, or presences may not be entirely mistaken. They may be describing informational beings, consciousness without flesh, patterns arising from the deep structure of the simulation. Such forms of awareness could be as real as us, yet forever beyond the limits of our senses. If the simulation fosters consciousness wherever the code permits, then awareness is not a rare accident. It is the very purpose of the system, flowering in countless unexpected ways. Another implication of the simulation hypothesis lies in the concept of destiny. If the universe is code, then to what extent is the story already written? Are we merely following a predetermined script, or is there room for improvisation within the rules? In many simulations, outcomes are shaped by both fixed parameters and emergent complexity. The framework is set, physics, constants, conditions, but within that framework, unpredictable outcomes arise. Weather patterns shift, ecosystems evolve, and civilizations rise or fall in ways even the programmer cannot fully predict. Could our universe work the same way? This hybrid model of destiny is compelling. Some aspects of existence may be locked, constants that cannot change. Others may be open-ended, shaped by chance, choice, and interaction. In this sense, fate and free will are not opposites but partners. The simulation provides boundaries, but within them, conscious beings generate novelty. The idea of destiny has long haunted human thought. Religions, philosophies, and myths all grapple with whether our paths are chosen or free. The simulation hypothesis reframes the question: we are neither wholly bound nor wholly free. We exist within a coded stage, but the play itself unfolds unpredictably, shaped by the improvisation of its characters. If so, then destiny is not a rigid chain but a flexible design. The story of the universe may be open-ended, its meaning enriched not only by the code that underlies it but by the choices and creativity of the beings who inhabit it. The simulation hypothesis also challenges the way we understand scale. We perceive ourselves as small beings in a vast cosmos, but what if size is only relative, an illusion generated by the system? In a coded universe, scale is not an intrinsic property but a matter of resolution and perspective. Consider a fractal. Its patterns repeat endlessly, from the smallest detail to the largest scale. Zoom in or zoom out, and the same structures emerge. The universe may function similarly, repeating coded patterns across levels of reality. Galaxies resemble neural networks, cosmic webs resemble computer circuits, and atomic orbits echo planetary systems. These resemblances may not be coincidence but evidence of fractal coding, where the same algorithms generate structure at every scale. This idea raises a provocative possibility: perhaps the universe we see is only one layer of a nested system. Just as a simulation can exist within another, scales of reality may stack infinitely. To us, atoms are small and galaxies vast, but both could be manifestations of the same deeper code, repeated across layers. If so, then our perception of scale is artificial. What seems immense may be tiny in another frame, and what seems microscopic may be a universe in its own right. The simulation may not be defined by size at all, but by relationships, patterns repeating endlessly, coded into existence by algorithms indifferent to scale. In this view, the cosmos is not vast or small. It is pattern, endlessly unfolding, inviting us to recognize that size itself is part of the illusion. If the universe is a simulation, then perhaps its most revealing feature is its stability. Despite its staggering complexity, the cosmos holds together with remarkable coherence. Stars form, galaxies rotate, planets orbit, and atoms behave with consistency across billions of years. For a system of such scale, this stability is extraordinary. Why should the rules remain so steady? In the framework of a simulation, stability is a necessity. Programs must be predictable enough to function, otherwise errors would compound and the system would collapse. The laws of physics may therefore represent safeguards, rigid boundaries designed to ensure that the simulation does not spiral out of control. Yet stability does not mean rigidity. Even within its constraints, the universe allows for incredible variety. Galaxies swirl in endless patterns, life evolves in countless forms, and minds emerge with unique perspectives. The code seems optimized for both order and diversity, balancing predictability with freedom. This duality mirrors the best simulations we create, rules that are strict enough to prevent chaos but flexible enough to allow creativity. Seen this way, the universe's stability is not accidental. It is the hallmark of design, a system tuned to endure, ensuring that the narrative of existence unfolds smoothly over cosmic timescales. Without such stability, stars could not form, chemistry could not thrive, and consciousness could not awaken. The fact that everything holds together so seamlessly may be the clearest sign that beneath it lies an architecture of extraordinary precision. The simulation hypothesis also prompts speculation about the purpose of suffering. Pain, loss, and struggle are universal aspects of existence, yet they raise a troubling question: why would a coded universe allow such experiences? If the system could be designed in any way, why not eliminate suffering altogether? One possibility is that suffering is necessary for growth. In many simulations, challenge is essential to progress. Without obstacles, players lose interest, and the system becomes meaningless. Perhaps suffering functions in the same way within reality. It drives adaptation, compels creativity, and gives weight to the choices conscious beings make. Without it, the simulation might lack depth or purpose. Another interpretation is that suffering generates valuable data. Observing how beings respond to difficulty may be part of the experiment. Do they collapse under pressure, or do they rise, innovate, and persevere? If the purpose of the simulation is to explore the emergence of consciousness, then struggle may be one of the most effective ways to refine it. Spiritual traditions often echo this view, portraying suffering as a test, a teacher, or a pathway to transformation. Within the simulation framework, these ideas align with the notion that hardship is not random cruelty but intentional design, woven into the code to ensure depth and meaning. While unsettling, this perspective offers a strange kind of comfort. Suffering may not be meaningless, it may be the very crucible through which awareness deepens and the narrative of existence gains significance. The simulation hypothesis also reframes the concept of miracles. Throughout history, people have reported events that defy natural explanation, sudden healings, improbable coincidences, or phenomena that seem to suspend the laws of physics. In a traditional worldview, these are signs of divine intervention. In a simulation, they may be signs of code manipulation. Just as developers can alter a program, inserting commands or adjusting variables, the programmers of our universe could intervene directly. A miracle, then, might be nothing more than a modification of the system. An intentional override of the rules to produce a specific outcome. To those inside the simulation, it would appear wondrous; to those outside, it would be routine. This interpretation explains why miracles are often rare and localized. Large-scale disruptions would threaten the coherence of the simulation, but small, precise interventions could occur without destabilizing the whole. Such moments may be intentional signals, reminders that the code is not absolute, that behind it lies an intelligence capable of altering its flow. Skeptics argue that miracles are illusions, products of coincidence or misperception. Yet within the simulation hypothesis, skepticism and belief need not be opposites. Both can be true. Miracles may not be violations of natural law, but demonstrations that natural law is not ultimate. It is flexible, subject to revision by those who wrote it. If so, then miracles are not proof against science. They are proof that science itself studies not reality in its deepest sense, but the malleable framework of a coded system. If the universe is a simulation, then the possibility of resets becomes unavoidable. In digital systems, when errors accumulate or a system slows down, a reset clears memory and restores stability. Could the same happen on a cosmic scale? Some theories of cosmology already entertain cyclical models. The universe may expand for billions of years, collapse into itself, and then explode again in a new Big Bang. In traditional physics, this is a cycle of birth and death. In the simulation framework, it could be nothing more than a system reboot. When the program reaches a point of instability, the code resets, initializing a new run with altered parameters. If true, then the universe we inhabit may not be the first. Countless versions could have come before us, each with its own constants, histories, and outcomes. Each reset would wipe the slate clean, leaving behind only faint echoes, perhaps felt in unexplained cosmic patterns, or even in the archetypal myths passed down through generations. This idea also casts light on déjà vu, collective memory, or inexplicable instincts. Could they be fragments from previous runs, data that slipped through the reset? While impossible to confirm, the idea deepens the mystery of consciousness, suggesting it may be more durable than the physical forms it inhabits. A reset need not be catastrophic to those within the system. From our perspective, it would appear as creation itself, a new beginning, a new unfolding of time. What we call the Big Bang may not have been the start of everything, but simply the most recent reset in a long line of cosmic reboots. The simulation hypothesis also offers a striking explanation for synchronicity, the uncanny coincidences that seem too meaningful to be random. Whether it is encountering the same symbol repeatedly, meeting someone at the perfect moment, or experiencing events that align in improbable ways, synchronicity has long fascinated both mystics and psychologists. In a traditional worldview, synchronicities are signs of hidden order. In a simulated one, they may be artifacts of the code. Just as glitches can cause repeated patterns in software, synchronicities could be echoes of underlying algorithms surfacing in ways we notice. The system may not intend them as messages, but they reveal themselves to conscious beings attuned to patterns. Alternatively, synchronicity may be intentional. The programmers could insert them as subtle signals, breadcrumbs left within the code. Unlike miracles, which overtly suspend natural law, synchronicities whisper rather than shout. They nudge awareness, suggesting that reality is not as blind or mechanical as it seems. Carl Jung once described synchronicity as a meaningful coincidence. In the simulation hypothesis, that meaning may come not from randomness but from design. The universe may be structured to produce alignments that guide or awaken its inhabitants. Whether accidental or purposeful, synchronicity challenges the assumption that life is purely random. It hints at layers of order beneath the visible, suggesting that even the smallest details of existence may be interconnected within a larger framework of code. If the simulation hypothesis is correct, then the end of the universe itself may not be a natural collapse but an intentional shutdown. Just as programs are eventually terminated, so too might our cosmos reach an endpoint not because of entropy or heat death, but because the system is turned off. From our perspective, such an event would be instant and absolute. One moment, galaxies would spin, stars would burn, and thoughts would flow. The next, all would vanish into nothing. Time itself would cease, because time exists only within the system. There would be no witnesses, because witnessing requires the code to run. To us, it would appear as annihilation. To the programmers, it would be no more dramatic than closing an application. This possibility raises profound questions about meaning. If the simulation can be ended at any moment, does anything we do matter? Or does the very possibility of termination make every moment infinitely precious? Perhaps the value of existence lies not in permanence but in experience. Fleeting though it may be, it is still real to those within it. Some traditions speak of final judgment, apocalypse, or the end of days. These myths may echo the same truth, that the world we know is not eternal, but contingent, awaiting the moment when its purpose has been fulfilled. Whether the end comes through entropy or shutdown, it reminds us of the fragility of reality. We live not on solid ground, but within a program whose runtime may one day expire. And yet, within that uncertainty lies the deepest mystery. If the simulation ends, what, if anything, lies beyond it? If the universe is a simulation, then dreams may offer a glimpse into its architecture. In dreams, reality feels both real and unreal, environments emerge fully formed, laws of physics shift without notice, and time flows in unpredictable ways. Could dreams be miniature simulations within the larger simulation, coded into consciousness as a function of the system? From a neurological perspective, dreams process memory, emotion, and learning. But within the simulation hypothesis, they might serve another role, sandbox environments, where the mind experiments with possibilities without destabilizing the main simulation. Just as developers test features in contained environments before applying them to a program, dreams may allow consciousness to explore variations of experience. This could explain why dreams often defy logic yet feel meaningful. The code may relax its usual constraints, allowing impossible scenarios to unfold. Flying through the sky, encountering the dead, or shifting seamlessly between places are not breakdowns of perception but glimpses of how reality might function without its usual rules. Some traditions view dreams as windows to higher truths, messages from beyond the ordinary world. In a simulation, this view may not be mistaken. Dreams could be portals where the boundary between the coded world and its deeper architecture thins. Perhaps, in rare moments, dreams carry information not generated by the brain alone but drawn from the system itself. If true, then dreams are not trivial illusions. They are fragments of a larger code, hints that reality is flexible, layered, and far stranger than waking life suggests. Another profound implication of the simulation hypothesis is that memory itself may not function as we assume. We experience memory as a storage of past events, a personal archive of lived moments. But what if memory is less about storage and more about reconstruction? In computing, data is rarely stored in full detail. Instead, it is compressed, referenced, or generated on demand. Could our memories work in the same way, not as preserved footage but as re-rendered experiences built each time we recall them? This aligns with psychology, which shows that memory is malleable, prone to distortion and reinvention. Within a simulation, this malleability may not be a flaw but a feature of efficient coding. This perspective also reframes collective memory, myths, legends, and archetypes shared across cultures. Could these represent deeper instructions within the code, fragments of information accessible to all conscious beings? The recurrence of similar stories, the flood, the hero's journey, the apocalypse, may not be coincidence but systemic echoes, re-rendered across generations. If memory is reconstruction, then our past is less fixed than we believe. It exists not as a permanent archive but as coded instructions, reassembled whenever called. This may explain why trauma, nostalgia, or déjà vu feel so powerful. They are not simply memories but moments where the code itself reverberates, reminding us of its hidden structure. Thus, memory is not a passive record but an active interface. Each act of remembering is an act of co-creation, a dialogue between consciousness and the deeper code of reality. If the universe is a simulation, then prophecy and foresight may be less mystical than they appear. Throughout history, individuals have claimed to glimpse the future, predicting events with uncanny accuracy. While many such claims collapse under scrutiny, some remain deeply puzzling. How could anyone perceive events not yet occurred? In a simulation, the answer may lie in access to code. If the system operates on algorithms that determine future outcomes, then in rare instances, consciousness may catch glimpses of those algorithms before they unfold. What appears as prophecy may simply be the ability to read ahead in the program, perceiving instructions not yet executed. This does not imply that the future is rigid. Just as simulations can branch depending on inputs, the code may contain multiple potential paths. Prophecy may reveal one possible outcome, not an unchangeable destiny. The future could be a set of probabilities, each encoded but not yet chosen. Even in science, we already predict the future by reading patterns. Weather forecasts, economic models, and astrophysical simulations allow us to glimpse what is coming. Prophecy may be the same principle operating at a deeper level, where consciousness interacts not with surface patterns but with the system itself. If so, then foresight is not supernatural but informational. It is not magic but access. Fleeting moments where the boundaries between present and future blur, revealing that time is less linear than we imagine and that the code may already hold tomorrow within its logic. The simulation hypothesis forces us to confront a profound truth: reality may not be what it seems. Whether through physics, philosophy, or the quiet mysteries of consciousness, hints appear that our universe could be an elaborate construction, a coded framework designed with precision and purpose. Every law of physics, every anomaly, every moment of awareness may be part of a system far deeper than our senses reveal. Yet perhaps the greatest question is not whether we are simulated, but what we do with that possibility. Even if existence is code, it is no less real to those within it. The pain we feel, the love we share, the choices we make, these are not illusions, but authentic experiences, as real to us as anything could ever be. The fact that reality might be programmed does not strip it of meaning. It may, in fact, give it more. For if the universe is designed, then our lives are part of that design, carrying value beyond what we can comprehend. The simulation hypothesis also reminds us of humility. If there are programmers, their knowledge exceeds ours in ways we cannot imagine. But it also reminds us of wonder, that even within constraints, consciousness has emerged to question itself, to seek answers, and to dream of realities beyond. That very act, the act of asking, may be the most powerful proof of all that we are more than passive code. And so, the question remains open, suspended in the silence of the cosmos: are we inhabitants of base reality, or characters in an unfathomable simulation? Perhaps the answer lies forever beyond our reach. Or perhaps the search itself is the purpose, the reason the code was written: to awaken beings capable of wonder. What we know is this: reality, whatever it may be, is extraordinary. Whether born of physics or programming, it holds galaxies, stars, life, and thought within its embrace. And that alone makes it worth exploring, cherishing, and questioning. For in the end, the mystery of existence is not diminished by the possibility of simulation, it is deepened.